Okay, so there are three phases of matter: solids, liquids, and gases. And chapter 13 is about liquids. Now I want to start off actually by reviewing atoms and elements, molecules and compounds, and density. And then we'll get into the chapter 13 material. So atoms are the building blocks of all matter. Everything's made of atoms. And they're way too small to be seen with visible light. Even in 1 teaspoon of water, it contains about 10 to the power 23 atoms. So they're very, very tiny. And they were first directly observed in these micrograph images of chains of thorium atoms in 1970. So an atom actually has some internal structure. It contains a nucleus, which is even smaller than an atom, very tiny part of the atom, which contains nearly all its mass. And the nucleus is surrounded by orbiting electrons. So in the nucleus are neutrons and protons, which in turn are actually made of smaller quarks. But what you need to know is that protons have electric charge +1, and electrons have electric charge -1. So most atoms, almost all the atoms in the world, have exactly the same number of orbiting electrons as protons in the nucleus, so that the charges cancel out. So atoms refer to the particles that make up a substance. If it's an elemental substance, that means it's only got one kind of atom in it. So this blimp is filled with hydrogen, which is the lightest and most abundant element in the universe. There are about 115 elements known, 90 of which occur in nature, and others are unstable, so they only get produced in the laboratory. And often the words atom and element are kind of used interchangeably. Here is the periodic table of the elements listing all those 115 different kinds of atoms. There's potassium, gold is on here somewhere, there it is, Au, silver. All of these are elements. So molecules form compounds, and this is when two or more atoms are bonded together. So, for example, O2 is molecular oxygen, two oxygens bound together. NH3 is ammonia, one nitrogen with 3 hydrogens around it. Here we have a carbohydrate, I think that's methane, CH4, and here is H2O, so water. Speaking of water, here's a bottle of water. I want to define density as being the amount of mass per unit volume of a material. So mass divided by volume. The units of density are kilograms per meter cubed. It's the sort of standard SI unit. You can also measure it in grams per centimeter cubed, which are not the same. So water has a density of 1 gram per centimeter cubed. You might be familiar with that, but it's 1,000 kilograms per meter cubed. Pressure is defined as the force per unit area that one object exerts on another. So the equation is force divided by area. If you take as an example these two bricks, they're both exerting the same force on the table if they're the same weight, but the pressure of this brick standing on its edge is greater because that same force is distributed over a smaller area. And if you really, really shrink the area, like at the point of a pin, you can have a very high pressure, and this is what causes pain, actually. It's pressure, not force. And the units of pressure are newtons per meters squared, and there's a special name for that. It's called the Pascal. 1 Pascal is 1 Newton per meter squared. So in a liquid, the force per unit area that a liquid exerts on its container is called the pressure. And the pressure depends on depth. Okay? So for example, here's a large but shallow lake. If it's 3 meters deep, it has some pressure at the bottom of that lake. If you have a small but deep pond, the pressure at the 3-meter depth will be the same as the pressure at 3-meter depth in the shallow lake, and it will continue to increase. So at the bottom of the pond, it's twice as much pressure as at the bottom of this lake. So pressure is a scalar number, meaning it doesn't have a direction. It just exerts pressure in all directions at every point. For example, if you tilt your head around underneath the water, it doesn't matter what direction your ears point, they still feel the same pressure. And if you have a bag and you squeeze it, the water will squirt out all directions. So it's always pushing against walls of a container. The bottom of a boat is pushed upwards by the water pressure. Same as a beach ball. If it's under the water, then that bottom surface feels an upward force. So buoyancy is the apparent loss of weight of a submerged object. So if part of an object is underwater, then it will seem to weigh less. And that is because there's pressure surrounding this object, pushing inwards on it, and the pressure on the bottom surface is a little bit bigger than the pressure on the top surface. It turns out that the buoyancy force, which is always upwards, equals the weight of the water that's displaced by the object. So the displacement rule is that when you have a completely submerged object, it displaces a volume of the liquid equal to its own volume. For example, this stone hanging in the container that was originally filled to the brim will displace some volume of water, which will pour out when you dip it in there, and the volume of this water equals the volume of the stone. So note that the buoyant force is equal to the weight of the water displaced, and that doesn't depend on how deep the object is. So the deeper an object goes, the more pressure it feels, but the difference in pressure between the bottom and the top surface is always the same, and that's the buoyant force. It was Archimedes that discovered this rule about buoyancy, which is that an immersed body, completely or partially, is buoyed up by a force equal to the weight of the fluid it displaces. That's called Archimedes' Principle, discovered in 250 BC. And he shouted "Eureka" when he figured it out. Archimedes' Principle applies to both gases and liquids. So here's an example. The apparent weight of a submerged object is equal to its weight out of the water minus this upward buoyant force. So, for example, we have a block here hanging from a spring scale, and the block weighs 3 newtons when it's outside of the water. You dip it into the water, and you'll find that its apparent weight is now down to 2 newtons, because there's an upward buoyancy force of 2 newtons on it. And the water displaced has a weight of 2 newtons. The fact that those are equal is Archimedes' principle. The principle of flotation is that a floating object up on the surface is displacing an amount of fluid equal to its own weight. So, for example, if you have a block of iron, it might displace 1/8 of a ton of water. So if the iron weighs 1 ton, then since iron is 8 times more dense than water, it displaces 1/8 of a ton of water and it sinks. But if you make that into a bowl shape, it will displace its own volume plus this whole big volume of air until the amount of water that displaces equals the weight of the iron, and then on the float. That's how the Titanic floats on the top of the water. So another result of Archimedes' principle is that denser fluids will exert a greater buoyant force on a body of the same volume than less dense fluids. So, for example, objects float higher in salt water, which has a density of 1.03 grams per centimeter cubed, than in fresh water, which has a density of 1.00. Archimedes' principle does apply in air, and we'll learn more about this in the next chapter, but the more air an object displaces, the greater the buoyancy force on it. If an object displaces its own weight, it hovers at a constant altitude. If it displaces less than its weight in air, then it descends. So what makes an object float or sink? It depends on the weight of the object and the weight of the fluid displaced. And the weight of the fluid displaced depends on the volume of the object. So what really counts here is the weight of the object per volume. And that, as we remember, is density. So the rules are 1, 2, 3. An object that's more dense than the fluid that it's in will sink, like this anchor. An object that is less dense than the fluid it's immersed in will float, like this piece of wood. An object with a density equal to the fluid will just kind of hover at whatever altitude it was, like this fish. Pascal's principle states that any pressure change at any point in an enclosed fluid is transmitted undiminished to all other points of the fluid. For example, if you press down on this end of a piston, which is a cylinder containing water, and a cap, press down on the cap, that will apply a pressure to the fluid underneath, and this pressure will end up pushing upwards on this cap over here. And this is how a hydraulic press works. The pressure applied to this left piston is transmitted, same pressure, to this right piston. So that if the area is smaller, 10 times or 5 times smaller on this side than on this side, then the force can be, well, actually it's 50 times. The area is 50 times bigger here, then the force can be 50 times bigger. You can support a bigger mass. Lastly, I want to talk about surface tension. Surface tension is a contractive tendency of the surface of liquids. So, for example, you take this wire that's bent and you pull it out of the water. You have to pull a little harder just when the wire reaches the surface to pull the wire out. Also, if you have a paintbrush dipped in water and you pull it out, all these hairs get pulled together by the surface tension when you pull it out of the water. Surface tension is caused by molecular attractions. So every molecule is attracted to all its neighbors, but up on the surface, the only neighbors are below. So there's this net downward force of all the surface molecules. And this causes the surface tension. It tends to contract a surface. So capillarity is one of the results of surface tension. We have adhesion between the molecules of the water and the solid glass tube that's dipped into the water. And then surface tension will try to shrink this surface so that inside a glass tube, shown in cross-section here, the water tends to be pulled upward until the force of surface tension equals the weight of this lifted column. Okay, the last two chapters were called solids and liquids. So if you guessed that this chapter would be called gases, then you're right. I want to talk about the atmosphere, atmospheric pressure and how we measure it, Boyle's law, and buoyancy of air, Bernoulli's principle, and plasma. So we are surrounded by an ocean of air, and this air exerts pressure. And these two little hemispheres are not glued together, but they're just pressed together and all the air has been pumped out. So these two guys are trying to pull them apart, but they can't. And the reason for that is that this ocean of air around us is pressing inwards on either side of this hemisphere and holding it together. So this just shows how much air pressure there is. Air pressure is caused by the weight of the air above us, and it can vary from one place to another on Earth. And in fact, measurements of air pressure can be used to predict weather conditions. So pressure is exerted against bodies that are immersed in the atmosphere, and it results from the weight of the air above us. And it turns out that here on Earth, around us right now, the atmospheric pressure is 101 kilopascals. You learned previously that a pascal is 1 Newton per meter squared. So that means every 1 meter squared of area is being pressed down with 100,000 newtons of force. That's almost the weight of 10,000 kilograms or 10 tons, so it's quite a lot. But I guess since it's around us all the time, we don't even notice it. One consequence of atmospheric pressure is that we can use suction to pump things. So if you pump out a vacuum, then the air pressure can actually push a liquid up a straw or up a big tube. And it turns out that if you have a big column of water being pushed up, then if that column of water is 10.3 meters high, then the pressure at the bottom is the same as atmospheric pressure. And so that's as high as the atmosphere can be used to push water. So above that limit, you have to use some sort of a mechanical pump. A barometer is a device used to measure atmospheric pressure. And what it is the column of mercury, liquid metal in a tube, and above it is a little bit of vacuum or a little bit of mercury vapor. And then it's sitting in a dish which is exposed to the atmosphere. And the height of the mercury column tells us the atmospheric pressure. And atmospheric pressure can actually decrease if you go up. So a barometer can be used as an altimeter to measure your altitude. But the basic principle is that this column of mercury exerts a pressure on the mercury in the dish, and that's equal to the atmospheric pressure. And when they're equal, it turns out that the column of mercury is about 760 millimeters high. Boyle's law says that if you have an enclosed gas at some temperature, the pressure and the volume of the gas are inversely proportional, meaning that if you decrease the volume, you increase the pressure, or if you increase the volume, you'll decrease the pressure. We kind of know this intuitively. If we take a paper bag and we compress it, then the pressure in there will increase, and it might even pop the bag. And it is proportional, so that if pressure is doubled, the volume goes down by a factor of 2. So here is Hewitt's way of using font size to kind of give you the idea. PV before equals PV after. So a large pressure would correspond to a small volume. That's, if you change it to a smaller pressure, that would correspond to a larger volume. So we talked about Archimedes' principle back in the liquids chapter, but it applies to air as well as liquids. An object that is surrounded by air is buoyed up by a force that's equal to the weight of the air displaced. That's what's holding up this fish that's filled with helium. So when the weight of the air displaced by an object is greater than the weight of the object, it rises. And that's true for these helium balloons because they're less dense than air. When the weight of the air displaced by an object equals the weight of the whole object, like when it's being held down by these rocks, then it just hovers there in air. And if the weight of the air that's displaced by an object is less than the weight of the object, then it's not supported by the air. That's why you and I are not supported by the air, is that we displace a little bit of air, but we're much more dense than that, so we weigh more than the air we displace. So you can fill a balloon with gas, and that will hold up a balloon, and that can be buoyant if the gas inside has a very low density. So for example, a hydrogen balloon will rise up in the air. But hydrogen is flammable, so we don't usually use that. We use the next best thing, which is helium. That's an inert gas, so it's a little safer. But also, if you just heat the air, it turns out that high temperature air has a lower density than lower temperature air, and so that will also rise. And it will rise up to some point where the atmosphere has become less dense, and so it stops rising after a while because the weight of the air that's displaced is less. Bernoulli's principle, discovered in the 15th century, states that where the speed of a fluid increases, the internal pressure of the fluid decreases, and vice versa, meaning that if the pressure increases, then that corresponds to a fluid speed that's decreasing. And this applies, to a smooth, steady flow. So here is a picture of water streamlines going to the right, and for some reason in this tube, the cross-section has decreased, so it gets narrower here. So when these lines get closer together, the flow speed is greater, and this fluid on this side, or gas, is a lower pressure than the fluid on this side. So the wider flow speed is less, and the pressure is greater. And when it's narrower, the flow speed is more, and the pressure is less. Some applications: if you blow on the top of the surface of paper, the paper will rise up, and that's the reason for that is that the pressure of the moving air is less than the atmospheric pressure beneath it, so it pushes it up. Also, if there's wind blowing over the top of your roof, it can have an upward force on the roof. It can blow your roof off. The reason for that, again, is that this moving air has a lower pressure than the stationary air below. Lastly, I want to talk about plasma. Plasma is the fourth state of matter after solid, liquids, and gases, and it is basically an electrified gas. So all the atoms or molecules in a normal gas are neutral, meaning there's the same number of electrons as protons in every atom. But in a plasma, the atoms that have been stripped of some or more of the electrons, and so the atoms themselves are positively charged, and they are coexisting with free electrons. And the sun, for example, is made of plasma. Also, fluorescent lamps that you see have plasma in them. So high voltage will cause electrons to travel through the gas, ionizing the atoms, and also providing a conducting path to complete the circuit inside the lamp. And that current will excite some of the mercury atoms and cause them to emit ultraviolet radiation, which interacts with some phosphor in the outside of the glass that's holding the lamp, and that causes the whole thing to glow in visible light. This is also how plasma TVs work. So these TVs are composed of many millions actually of little pixels that are red, green, and blue, each containing a different gas. And these pixels are sandwiched between a whole network of little transparent electrodes. These electrodes are charged to produce electric currents, which generate light. It's ultraviolet light, which stimulates phosphors in the screen, and then which emit visible light that we see. And all these little pixels combine to make the image that we see on the television.